Okay, so I'm Jan Michalewski. I'm a PhD candidate in Stanford University in California. And I'll be presenting joint work with Suman Nath and Jai Lu from Microsoft Research. So the title is MASHaBLE, and it stands for Mobile Applications of Secret Handshakes over Bluetooth Low Energy. So, and I'll start with an explanation of the motivation. And first of all, I'll explain what I mean by secret handshakes. And then the implementation itself is over Bluetooth LE. So I hope most of you are familiar, at least basically, with what it means, and I'll explain that too. So it's very important to understand the motivation. That's the key to understanding why this is important and interesting and why it's useful. So do ask questions, interrupt me if you don't understand anything, and I'll try to elaborate. Okay, so yeah, let's start with the motivation. So recently we're experiencing increased user concern about privacy, not only from users that are into security and care about it, but also from the general public. There are widespread apps like Telegram and Signal that you might be familiar with, which provide end-to-end encrypted messaging, and there are additional applications that provide other privacy or anonymity features. So the motivation is multifold. Basically, we're interested in private communication and interaction between users in anonymous messaging. And we want to form what we call secret communities, basically secret virtual societies where users can enroll in the community and interact with other users, but they want to preserve their anonymity and privacy within the community. Yeah, we also want something that's based on physical proximity. Basically, we want those users that belong to those secret communities to interact with other users when they're nearby, to be able to discover them and later on interact with them. And we also want to provide message dissemination to those nearby users. And it doesn't only apply to the mobile setting, which we'll focus on, it also applies to, more generally, to Internet of Things devices and all kind of internet-connected devices. So yeah, so we have different messaging applications that were very widespread at a certain point, and probably the more familiar of them is Yik Yak. And what it provides is anonymous messaging within a community. That's based on some physical proximity. So basically, a user sends a message to the Yak server, and then the Yak server disseminates this message to users based on the location. So it checks the location of the user that sent the message, and then it forwards the message to users who are nearby. It can be something like a school campus, a university, or just some geographic area. And it strips the metadata from the message so that the other users that receive it don't know which user it came from. So it became a popular way to share all kind of private thoughts or whatever. Sometimes it's something more interesting and sensitive. Something is just some random stuff. But this was a very widespread application. And other examples are After School and Ligatalk, which were also popular on campuses and in schools, to the extent that teachers actually suggested banning them because people were able to interact in an anonymous manner. So one caveat here is that the Yak server knows everything about the users. On one hand, in terms of user experience, it seems like the user is anonymous, but basically you're sending a message to the Yak server, which forwards it, so the Yak servers know the origin of the messages, and that's a certain compromise to privacy. So building on this notion of anonymous messaging that's based on location, we want to form secret communities with this notion of physical interaction based on physical proximity incorporated into them. So to define secret communities more formally, let's take note of the following properties. So we have members that want to identify one another, and basically they don't have to meet each other beforehand in order to identify one another. Think about it as something like the Freemasons, or pick any other secret society you like. So basically you have people, a very loose organization, where you have some administrator or some head of the organization, users enroll, users basically join this organization, and then they want to be able to recognize one another when they meet each other. And they don't want to be discovered by anyone that's not in the community. So that's the privacy guarantee. We want it to be based on geolocation, and we want to maintain this geolocation privacy. So we basically don't want to, we potentially want to avoid sending our coordinates to some server that will notify us of users that also belong to the community that are nearby. We want to keep it as private as possible. And we want to facilitate anonymous messaging within the secret community and dissemination of notifications to the users. Okay, so one way to realize it would be using a trusted server. And the way would be for different users in the community to communicate with the central server. The communication can be secure, it can be over an encrypted channel with authentication and all of that. But, and basically send in the server both the content that you want to send to other users and also your location, so that the server can check who are the users that are close to one another and notify them of their proximity. And then the users can start interacting and pass content to one another. The problem is that in this case, the server becomes a target for attacks. So basically, what's called compulsion attacks, where you have a single point of failure, basically one point, which if you manage to attack successfully, you gain access to the whole system. You compromise the whole system. So if the evil attacker manages to get control of the server, it knows both all the metadata related to the messages passed and the content as well. It can know who are all the users that belong to the community, and it can also impersonate another user in the community. So that's one problem. And also the fact that you're communicating, even the communication itself with the server is problematic, because it basically reveals your affiliation with this specific organization. If people know that this server belongs to a certain organization and you're addressing the server, then you clearly has something to do with it. So you can use anonymity solutions like Tor, but that might complicate the setup. There are also all kind of attacks on Tor, timing attacks. So that's another point we would potentially like to avoid. There's another issue of internet connectivity, which might not always be available for mobile devices. Mostly you have it, but sometimes you might be in an area where you don't have good connectivity to a central server. So that's another issue. And the trusted central server approach also requires you to submit your GPS coordinates and requires communication. So both of these are major factors in terms of power consumption, in terms of the battery consumption of a mobile or a small IoT device. So a GPS is a very power-consuming sensor. And you can see the breakdown of the power consumption in these graphs. So that's another thing we would like to improve upon. So to summarize, we want to avoid interaction with the central server. We want to leverage physical proximity for the interaction we want to create between users. And we want to minimize energy consumption. So all of that suggests that Bluetooth Low Energy might be a good promising solution. So Bluetooth LE, or Bluetooth Low Energy, is a protocol that was designed with energy efficiency in mind. It was designed for communication between devices on a short range, meters or tens of meters at most. And it's super energy efficient. And you can communicate between different mobile devices, or you can also communicate, have some interaction between something that's called a beacon that transmits something, and other devices receive it, and they can reply to this beacon, or just be notified of something with some custom data that's placed in this beacon. So that's good, but first the devices, in order to support those secret communities, basically they have to be able to trust each other. Something that's secret, a secret society, basically implies some trust and some authentication between the users. So that has to be addressed first. So in traditional certificates, for instance, if I'm browsing to google.com, Google basically presents me, gives me a certificate that claims, hey, I'm Google, and here's some digital signature by some other root of trust that all of us trust, something like VeriSign, so you can verify my identity. And that's great, but that's not the case here, because here, the interactions between users that do not trust each other, and that they do not know each other, and they're also not willing to reveal their credentials and their identity before they can trust the other party. So there's a chicken and egg problem here. Basically, if we have Alice, and she's only willing to reveal her credentials to another party in the secret community, and we also have Bob that is in the same boat, we have a problem. None of them is willing to present some certificate first to prove its identity, and so we're kind of stuck here. So how do we break this loop? And the thing that we want is basically called the secret handshake. So think of a physical secret handshake. Let's go back to the Freemasons example. So we have some procedure in which we perform with another person, or in the cyberspace it will be a device that has the following properties. Parties do not know each other, and they perform a procedure that establishes trust. And if it fails, it has to reveal nothing, basically. If it doesn't succeed, you don't gain any information about the other party. So if I'm performing some secret handshake with somebody, I'm doing like something weird, and the other party doesn't understand it, it doesn't know what it is, so it doesn't gain any information about my affiliation with any community. But if it succeeds, if the other party is also involved with this community and knows how to reciprocate successfully, then we basically perform a handshake that reveals our affiliation with this group. And the nice property with the cryptographic secret handshakes that we'll use, kind of the cyber analogy to those physical secret handshakes, is that also enable us to establish respective roles within those groups. So I can introduce myself as some VIP member of this group, and another person can introduce himself as an administrator of some secret community. So things like that. So that's exactly what we want here. Is it clear so far? Okay, so let's go on. Cool, so before I describe how we do it actually, I want to mention some more applications that are related to BLE and how they can be enhanced with this secret handshake technique. So if you're familiar with iBeacon, that's basically a Bluetooth LE beacon that was standardized by Apple, and it can announce the presence of different devices, and it can be used for something like announcing some event. So a company named Double Dutch actually used the iBeacon to advertise events and perform head counting, basically count the attendance to the event. So the users would scan this for this beacon, would receive it and reply to this beacon, and the base station that would transmit this beacon would count the number of responses, and using that basically count the attendance. So that's nice, but it exposes the users and the event as well for tracking. So somebody, so far we didn't require any privacy guarantees, but if we want to make the event private, or the fact that I'm attending this event private, if it's something sensitive, then we would like to prevent tracking. So for instance, if there's an eavesdropper in the crowd and it's scanning for beacons, we don't want to enable basically disclosing the fact that somebody has attended an event, or even the existence of the event by scanning this beacon. So by introducing the secret handshake between the base station and the attendees, we can solve this privacy issue. So that's the example, that's kind of the illustration. You have the beacon, it's transmitted, received by users, and they reply to it. So if we introduce a secret handshake instead, we can increase the privacy. So yeah, so our implementation of the secret handshake is based on something called cryptographic pairings. So that's, as opposed to the Bluetooth pairing, which you might be familiar with, that's something different. That's a mathematical operation, and I'll explain it in a minute. And it possesses those exact properties that we want from a secret handshake. So if it succeeds, the parties know that they are affiliated with a common community. If it fails, no information is disclosed, provably. That's a cryptographic mathematical guarantee, so that's nice. And it's also collusion resistance, meaning if I'm a corrupt user from the community, I cannot collude with an adversary or with another user to impersonate a different user in this community. I only have my credentials. I cannot pretend I'm somebody else within the community. And the credentials are also compact, and by compact, I mean the actual size of the number of bytes we need to transmit in order to perform this procedure. So that's very important because on top of Bluetooth LE, we can only pass so much data. We have tens of bytes that we can transmit. That's very restrictive, so that's an important property. So let's go over pairings very briefly. We have a pairing is basically a mathematical pairing over elliptic curves, so it's related to elliptic curve cryptography. So it's basically a function that takes two inputs, and it has what's called the bilinear property. So if we have two inputs, x and y, that lie in certain algebraic group, and they're multiplied by some factors a and b, some integer factors, when we perform the pairings, we basically have this property that we can take those factors to the exponent of the pairing. So just take it as is. I won't explain why it is so, but that's pretty involved. But that's the bilinear property, and it turns to be very useful for many applications. So, for instance, if you're familiar with identity-based encryption or different broadcast encryption schemes, many of them use exactly this property. They're based on this bilinear pairing. And also short signatures, the BLS signature is also based on this kind of function. So now how do we use it to perform this secret handshake? So we have this group administrator. Think of it as the person that organizes this secret community. And he will possess what's called the master secret. So the person will pick this, or the device will pick this secret integer t, that it will keep to itself. And when this master wants to enroll new users into the group, they will interact with him. So they don't need to interact with one another beforehand. They just need to interact with the master to get their credentials. So, and we have a pair of credentials. One of them is the pseudonym. This, for instance, for Alice, it will be PA, and it's a random string that she will use for her public interaction. So it can be something that has some structure and some random part, something like that. And there's also TA, which is her secret credential. So she will keep it to itself. She will never transmit it or share it with anyone. And the TA is formed by hashing this string PA onto the elliptic curve and multiplying it by t. So basically TA is something that the master computes for Alice and gives it to her. And by the properties of elliptic curves, you cannot just infer t from knowing TA and the hash of PA. You cannot divide on elliptic curves. Okay, and the same goes for Bob. So he also gets this pair of credentials. So now what we have is that they exchange their pseudonyms, and then they compute, they derive the cryptographic shared secret key from using those pseudonyms. So you can see that each one of them hashes the pseudonym of the other party it received over the air, and pairs it with his or her own secret credential, the TA or TB. And by the property of pairings, and you can see it and check it with a pen and pencil later, we get that if they were derived using the same integer t, which is secret, they will basically be the same. Those two expressions will be equal. So in case they belong to the same community, they'll derive the same cryptographic key, which they can now use for encrypted to form an encrypted communication channel between one another. So what's left is to basically test that they actually derive the same key, and that you do by a simple challenge response protocol. So Alice sends some challenge to Bob. Think of it as some encrypted integer or anything else, any other way to do a challenge response, and Bob can simply reply with simply decrypt and reply with this number, random number +1, and that's a successful response to this challenge. And the same goes for the other way around. So Bob also sends his own challenge encrypted, and Alice has to respond. So once they both got the responses, they basically know that they're affiliated with the secret, with the same secret community. Okay, I'll skip some part here because we're short on time. But we also need to do something that's called tracking prevention. So if we always transmit the same pseudonym, we have a way of overcoming it by basically having multiple credential issued to us during enrollment with the group. So then for every interaction, we can use another pair of credentials. And if I'm using one credential at one place and I'm using another credential in another one, then they won't be linked. So you cannot infer the fact that the same user has been into different places. But what happens if you can infer it from a lower layer, basically kind of the MAC layer of Bluetooth LE? So if you're using the public device address that's constant, you'll be able to track the user. And exactly for this reason, we have in Bluetooth LE what's called the random device address, which can be set differently for every interaction, for every packet you transmit over Bluetooth LE. So that's something we need to, that's very important to use in order to prevent tracking for users. So how do we incorporate it into Bluetooth LE? How do we integrate this math into the actual Bluetooth LE protocol? And here, one proposal is based on the actual Bluetooth pairing. So just to not be confused, this is not the mathematical pairing. Now we're back to the Bluetooth pairing. So before devices start to interact with one another, they perform this pairing, which basically introduces them to one another, and then they have some encrypted communication channel. And there are a couple of different methods to do it. Some of them use a shared secret that's delivered to them separately through another channel. One method is basically this just works, doesn't provide any protection against man in the middle. That's just a simple Diffie-Hellman key exchange. And you're probably all familiar with this method that requires you to input some PIN code that you see on the other device into another device. So that's also a common method. What we propose is integrating our secret handshake using the existing messages of the Bluetooth pairing protocol. So we basically want to use them in a different way. Instead of passing the original content specified in the Bluetooth standard, we suggest to incorporate those pseudonyms that we've seen in the secret handshake before, and also the challenge response in the existing messages of the Bluetooth pairing protocol. So that's one suggestion, and it's fine, but that would require a modification of the Bluetooth LE standard. That would require some extension, and definitely quite a low-level access to and modification of the hardware or the software, depends on which layer in the stack it's implemented. But that's a pretty involved change. So that would be nice for future versions. But currently, we wanted to implement it on the Bluetooth LE stack as is. Basically, use the existing capabilities to perform the secret handshakes. So we ended up using what's called Bluetooth LE advertisements. And another name for an advertisement is basically a beacon. All the beacons, they're based on those advertisements. So that's something you can transmit constantly in a very energy efficient way, and other devices can scan for it. So scanning is supported by most mobile devices, and publishing advertisements wasn't supported by all of them at the time. At least at the time of writing, Android didn't support the advertisements de facto. It wasn't the API, but you couldn't do it on all the phones. Nowadays, we have Google Nexus 5 and on, and Nexus 6P. They all support publishing advertisements and control some content in this advertisement packet. And the best support actually turned out to be on Windows Phone 10, which enabled both scanning and advertising at the same time. And as much as I wanted to avoid developing on Windows Phone, I ended up using it because that basically provided us with what we needed. So these are actually small packets that enable squeezing a little bit of custom data into them. So originally 32 bytes, but there are further restrictions that depend on the operating system, the API, and on Windows Phone, we could basically control 20 bytes. So in those 20 bytes, we need to squeeze all those pseudonyms, challenge responses, whatever we had in the secret handshake. So luckily, because the credentials were compact, we were able to achieve 128-bit security with this size. So, and the implementations, before implementing it, we had a couple of considerations. We needed an easy implementation of the mathematical pairings. They're pretty involved, so we had this JPBC library, but we couldn't use it as is for Windows Phone. We needed support for Bluetooth LE advertisement publishing and scanning, obviously, but publishing. And Windows Phone ended up supporting scanning and advertising at the same time, which turned out very useful in order to implement this protocol. So we ended up using it. And what we used for the mathematical pairings was the Stanford PBC. PBC stands for Pairing-Based Crypto Library. We had to port it to ARM, and we also written a .NET wrapper for it that's called PBC Proxy. And that's kind of a nice byproduct of this project because it enables other pairing-based cryptography applications. So now you can take it and implement identity-based encryption, broadcast encryption, whatever you can think of that requires pairings. And also whatever requires operations over elliptic curves, so that's a nice byproduct. And the communication between the two phones is based on alternating between those states of scanning for advertisements and advertising yourself. And sometimes it happens in the same time, simultaneously. So that's a diagram that describes the protocol, and the terms advertiser and scanner are kind of arbitrary. They both perform scanning and advertisements. It just the advertiser is the one that sent its credentials first, its pseudonym first to the other device, and the scanner is the device that received it and now proceeds with replying to the pseudonym with his own pseudonym and proceeding with the handshake. So you can see that they alternating between those scanning advertisement states and compute the share keys at some points and then perform the challenge response. So the important part here is the evaluation. And what first of all, we needed to verify that functionally it works. So we have some protocol, we have some communication between two devices, and we need to make sure that there are no issues of missynchronization, and they can actually perform those handshakes successfully. So we conducted an experiment in which two mobile devices were running our application for more than 2 hours, and with frequently performing those handshakes. And out of more than like 1,068 handshakes, 1,025 of them succeeded. So it's a very high success rate. And the handshakes that did not succeed, they probably did not succeed because of some missynchronization issues between the two devices. So still pretty good. And the last experiment that's more important in terms of proving that you can actually go for a whole day and perform those handshakes between devices is the energy consumption evaluation. And once again, we showed that to summarize the result of this experiment, what it shows is that we can use a mobile device and go on proceed with those handshakes for a whole day, and we can still won't drain the battery completely. So we can actually practically use it nowadays. So the future work would be implementing it for Android, because now it's also supported by Android, and performing some optimizations that are related to the mathematical pairings. And what would be nice is also to use Bluetooth LE specific identifiers, basically the MAC layer of Bluetooth LE, to embed those pseudonyms instead of using the custom data in the advertisement packet, because using those fields that in the data link layer would enable us to have more space and use the advertisement packet data for some custom application content. And obviously develop more Windows Universal applications using this PBC proxy. So to summarize, we have those secret handshakes, and it's a provably secure primitive that has some useful applications. So we can increase privacy and security and enable mutual authentication between devices using this provably secure technique that's based on math. And we can easily achieve better security and privacy for mobile and IoT. So there's no need for us to expose the identities of different devices. If we can replace, if for many scenarios we can replace it with a secret handshake, that would provide this trust between parties that did not interact and did not publish their certificates beforehand. And the evaluation shows that the application is fit for practical use in mobile devices in terms of energy consumption. You can basically go for a whole day using it. So that's all, and I'll take questions if you have any. Yes? Again, can you repeat it? You mean this? You mean this one? Yeah. Yeah. Yeah, so I mentioned it's a very simple prototype, and we didn't particularly address going out of sync. So we exchanged some messages, and if the other device at some point misses the message, they can go out of synchronization, and the handshake might fail. You can easily solve it by using acknowledgement between the two devices. That would increase the number of messages, but it's pretty easily solvable, and you can reach 100% success. Yeah. Yeah. Okay, so yeah, the question is whether there's something special about elliptic curves and whether we can use a regular Diffie-Hellman protocol. So first of all, Diffie-Hellman is just a key exchange. And here we have kind of a key exchange, but the property we really need is this intractability of devising the secret. So that's similar to kind of a discrete log problem in multiplicative groups, but and another property we need is this property of the bilinear pairing. And for that you need, we only know how to implement pairings, bilinear pairings over elliptic curves currently. It doesn't mean that in the future we won't find another way to implement it, but currently that's the thing, so that's why we need elliptic curve cryptography here. Okay. Yeah? Any other questions? No? Okay, so thank you for attending, and the code is available online. We have a white paper that's going to be published under the conference proceedings, so welcome to take a look. Thanks.